Alright, hello and welcome to the series on making one MCP, which is this molecule here. This molecule we're interested in because it's able to stop apples and also pears and a few other fruits from aging by inhibiting their ethylene sort of processes. This is the correct structure of the molecule. In the previous video in this series, the introduction video, I actually drew the structure wrong, which is very embarrassing. I actually drew another structure wrong in it, but we'll get to that in later videos. I'm trying to be professional here and I draw the bloody structures wrong. But yes, the double bond is here, not down here. Anyway, this first reaction, what we're going to have to do is we're going to have to convert tertiary-butanol into isobutene. What I'm going to do first is we're actually going to talk about the mechanisms and the reason why this reaction works. It's not often that I talk about the theoretics behind a reaction, but this is such a classic textbook reaction that I wanted to talk about it. So this is an elimination reaction, and there's two things to consider here in terms of what makes a reaction favorable, and that's the leaving group and the carbocation stability. Carbocation stability, I'm going to say that correctly. First we're going to look at leaving group. So the leaving group is the assortment of atoms that you want to actually leave the molecule for the reaction to work. And the more stable the molecules are on their own, the more favorable it is for them to leave. That makes sense because if you have to disconnect it and you've got something really unstable, then that's not really, the energetics of that reaction isn't very stable. If you've got something that you can split apart, a molecule can split apart and get two stable molecules from it, then that reaction is going to be a lot easier to actually occur. In this case, what we really want is we want this OH group, this alcohol group, to leave. And it might be easy to think, oh, well, we can just sort of heat this reaction and drive the water off. And the OH group will just, fuck off by itself. The problem being, the OH group is a terrible leaving group on its own. And there's a couple of things that make a leaving group a good or a bad leaving group. And that's a lot of university talk in itself. But really, the more sensible a molecule is on its own, then the more likely it is to leave. So OH is on its own has got a negative charge on it, so OH minus. It's not a very good leaving group. In fact, it's a terrible one. It's a poor leaving group. So for this to happen without any sort of catalyst or anything with a heat, forgetting about the rest of the molecule, just to drive off an OH from any sort of molecule by itself just with heat, it's not going to happen really because the leaving group is so terrible. So how do we make the leaving group better? Well, what we can do is we can do this in very acidic conditions. So now what we're doing is we're doing it in the presence of H+, right? So a H+ is going to get attracted to, we've got some lone pairs on the oxygen here. And what that's going to do is electrons are going to go towards that H+. Don't worry if you haven't really seen electron pushing stuff before. And we're going to change this group, sort of transiently in a way, into, OH2. With a positive charge on it. Now, all of a sudden, instead of being a really poor leaving group, we've now got an excellent leaving group because this can leave and form, that's just water by itself. So that loves leaving. So by doing it in very strongly acidic conditions, we can turn an alcohol from a poor leaving group into a good leaving group. So that's this first point, that's the leaving group. So, we've turned our poor leaving group into a good leaving group, but we've got to say, what do we leave behind? And that's the next step here. So this is the overall reaction, but if we think about, if this water leaves, what are we left with? Well, we can draw, the transition state of this reaction over here. So the water's left, so we're left with this molecule here, which is 4 carbons and a positive charge on the molecule. So this is our carbocation because it's carbon, and it's a cation because it's a positive charge. Now, that doesn't look like a very sensible molecule, and in a way, they're not really. That's why they're transition states, because this is going to react further very quickly. What will happen is this H here, that will give up its electrons, and then you'll end up forming our target molecule, the isobutene plus H+. Which is what we use in the first place. So you can see how that cycle, we haven't actually used any charge in a sense. The H+ is just a catalyst for this reaction. A huge part of my university degree was actually carbocation stability. Really, the idea is that the more stable this molecule here is, the more favorable this overall process is, because that's sort of, in the activation energy, you have to form this molecule first, and then from there you can then release energy. But this is sort of the difficult part of the reaction in a sense. So we can investigate further into carbocation stability. So we have the simplest example of all the different types of alcohols we can have. So we've got primary, secondary, and tertiary. So we've got methanol, isopropanol, and tertiary-butanol. And we can look at what the transition state would be if we eliminated those alcohols. The big difference between all the carbocations is their stability, because the more carbons that are attached to the carbon with a positive charge, the more stable the molecule can be. I didn't explain that very well, but if you're in this central carbon and you say, oh, this carbon has a plus charge, that plus charge can sort of be shared between all the carbons. And so it's not like this huge, dead weight, positive charge on one atom like it is here. That carbon can't do anything about it. It has to have that positive charge. So this molecule, hugely unstable. This molecule is a secondary carbocation and is quite unstable as well. This is a tertiary carbocation and it's reasonably stable. And that's all about this sharing of the positive charge. So that's why this reaction is interesting, because we are doing an elimination reaction on an alcohol, but because it's a tertiary alcohol, we're able to do it at reasonable temperatures. And that's because this intermediate is a lot more stable than these other intermediates. We're going to get away with doing reasonable sort of room temperature reaction of this. This reaction here, especially for like doing ethanol to ethylene with an acidic catalyst, it's hundreds of degrees. It's quite high. Same with this reaction. It's quite high because you're making an unfavorable intermediate. Because of the reasonably favorable intermediate, it's still unfavorable, but it's because that carbon can share the positive charge, it's not terribly unfavorable. And because we're making that a good leaving group, because of the H+, we can make this reaction happen. All right, I think that's definitely more than enough theoretics for one day. Let's get into actually doing some of the chemistry. So the chemistry we're doing today isn't actually all that complicated. The problem being is that the boiling point of our product, isobutene, is -8 degrees. I've never done something like this before, as in like distilling something with a boiling point below room temperature, and it's quite a lot below room temperature. You might think, oh, -8, that's, you could get down to 0 with ice and then you're basically there. Well, the problem is the day I've picked today, or most days are like this at the moment, is actually, we'll come back to the setup a bit later, but if we have a look at our thermometer, we can see the temperature is 38, 39 degrees. So -8 is quite a lot below 38 degrees. So we've got a long way to sort of go down from room temperature. To help us along, we have a few kilos of dry ice, a chemical I've only ever actually had once here in the lab. And at that point, we just dicked around with it. So I got that. We've got some normal ice too. So through the pump here, we obviously want it to be very cold. However, it's going to run off this little small pump here, which has been the workhorse of the lab for the last, ever since it started, really. It's all made of plastic and stuff, so I don't really want to take it down too much, as in to actual dry ice temperatures. And I don't really want to pump too many other solvents through it that aren't water, like I'm not going to obviously pump acetone through it, because it is sort of just shitty plastic at the end of the day. And if this fails, the whole synthesis is cactus, because I don't have a backup pump or anything like that. So I've got a whole lot of ice and a whole lot of calcium chloride here. I bought a new pack. This was the cheapest calcium chloride I could find at the hardware store. This was $15 for 3.4 kilos, which isn't dirt cheap, but I still think it's pretty good and allows us to use a lot, because we can get solutions of calcium chloride down to temperatures like mid -40s nearly. With a whole lot of ice, a whole lot of calcium chloride, and they help with a little bit of dry ice, we should be able to pump really cold water through here, much colder than -8. Well, not a whole lot colder, but enough to mostly condense it. And in here, we'll fill this with dry ice so that the stuff does still come down basically into the flask and condense. We don't have to condense every single bit that comes over, because we're not too worried about tertiary-butanol. We got enough of that, so we can just keep it going until we condense a whole lot, but we should be able to condense quite a lot of it. Alright, and after all that, let's see if the thing actually pumps. Plug it in. Oh, it's actually working. Amazing. We'll let that get cold. That's good, that's good, that's good. Alright, so while everything is cooling down, let's actually put some chemicals in our apparatus. So the first one to go in is sulfuric acid. So I'm actually using 50% sulfuric acid because apparently this is enough to get it working. Dilute sulfuric acid is enough to do this elimination reaction. Next to go in is 50 mils of tertiary-butanol. 100 mils of sulfuric and 50 mils of this. You can tell they're just arbitrary numbers. It doesn't really matter with this sort of reaction. Of course, if you're elsewhere in the world, you probably would have to worry about tertiary-butanol being a solid at the moment, seeing as it melts at 24 degrees. Being 38, I keep pointing that out, but oh god, I'm sweaty. Actually, you haven't noticed already, the best bit about this video is the coloured gloves are back. I found them again. So ignore the sweatiness under the gloves. But alright, everything's set up except for the dry ice bit, which we shall do now. Got this, got our cute little scoop. We'll take some here. Spill it everywhere. We've got our flask in here, we've got a whole lot of rocks because just to fill up the space, not really for aesthetic reason. Aesthetics. You know, I can't really pronounce words too good, but that's not what you're here for, so. This is a lot of fun. I'll be honest. This is a lot of fun. I do have some ethanol to pour in there, but I think it should be alright just with the dry ice. We'll put the lid on, or the resemblance of a lid. So our receiver flask is in dry ice. The water pumping through it is at least -10 or below. We measured that. The water bath here is at 50 degrees, pretty much exactly. So let's go ahead and add some of our tertiary-butanol and see if any of the magic actually happens. Alright, I'm going to add a whole lot more of this because there's not really a reaction happening at all. So, well, I've added all the tertiary-butanol and it's kind of working. I can see a little bit of bubbles, but you can possibly see that on camera if we focus correctly. Yeah, you see that little bit there? So I don't think it's quite hot enough for the azeotrope to boil off yet. Where are we at? What I'm going to do is I'm going to add some concentrated sulfuric acid in here now that I've got the, got the addition funnel here anyway, and that should kick it off a bit faster. Obviously needs a little bit more concentrated acid to happen, or higher temperatures. But if we do higher temperatures, then we start to boil off the tertiary-butanol azeotrope. I should probably go over the setup just a little. So we've got the addition funnel, the Kleisen adapter. It's all a little bit complicated, more complicated than it needs to be. But Jesus, I just wanted to use all this glassware for a change, especially the Kleisen adapter. I don't even know if I'm pronouncing it right. That's how often I use it, which is never. I don't think I've ever used it before. And I have one. So, and we've got our Vig Rao column. And the condenser, and then down there. So ideally what would you do is here, instead of the column, we'd have another condenser, and I'd hold that like room temperature, so it would cool down any tertiary-butanol, water, or the azeotrope between tertiary-butanol and water, but it would let through our product. I don't have two pumps to do two different condensers, so we've got the column here, which is effectively acting as an air condenser. It would stop it from the tertiary-butanol from making it to our end product. So that's why this setup is unusually tall, and I don't have a manifold, so that's why I've got a huge banana box. People on Twitter pointed out how appropriate a banana box is when we're trying to make the methyl cyclopropene, so I didn't even think about that. But yeah, it's quite a curious setup, but it's working fine. Well, I mean, it's not working at the moment, but so we're going to add some concentrated sulfuric acid, but we can't let the temperature rise too much. Concentrated sulfuric acid is here. As you can see, it's a bit dirty because it's like the pre-distillation sulfuric acid. So I don't really throw out much sulfuric acid in the lab. Where I can, I sort of recycle it. So I collect it all together, concentrate it, and then put it in a flask and boil it over. But this is the stuff that's like left in the flask, because it's hard to boil sulfuric acid solution dry because they start to bump really violently. So this is the stuff left in the flask after the distillation, in the distillation flask itself. It looks dirty, and it is dirty, but it's fine for methods like this. That's why I can use it. So I have, out of that distillation, sort of half of it will become clean, nice distilled sulfuric acid, but then the other half will remain dirty, and they're both useful in their own right. Hopefully we don't get too much of a temperature spike, because we know how exothermic sulfuric acid likes to be. It's hard to see if anything's happening in there. It's all cloudy now, which I think might be a good sign. I think it's working, but we're getting nothing condensing, so I'm going to chuck some dry ice directly into the water bath, which will cool it down without actually diluting the calcium chloride content of the water. So hopefully it doesn't freeze it, because we still need to actually pump it through the condenser a bit. Oh yeah. Well, that phase separation probably isn't helping at all. It's been like an hour and I still haven't got it to produce any bubbles. I just thought it would work. Theoretically, it's really not that difficult. Maybe I need better stirring or something, because maybe it's just phase separating and it's not mixing properly. Alright, well, it's not really working in the slightest, and I think it's just because we're really not making any of our gas that we want to, and I still don't know why that is. The temperature of this is quite high at the moment. It's really, you know, way above even the boiling point of tertiary-butanol, so I don't really know what's happening. One thought I have, possibly you could add a bit of water to this, because perhaps it's the acid is too concentrated. I don't know why that would help, but we'll try it, and if not, we'll just have to dump this reaction mixture, because I've got the dryers today and it takes me, you know, over an hour and a half to drive to get it. That's the closest place I can get it from, so I really have to do this reaction today or wait a while, because I don't really enjoy doing that drive. Alright, as I've been adding water, I think it's been getting better. I've now got a distinct sort of smell of at least a sort of a butane-like product. There's a tiny little bit of liquid in the bottom of this flask in here, but it's very hard to see because of all the dry ice, but it's definitely less than a mil. And this flask is full, so what I'm going to do is I'm going to decant out half of it, and then we're just going to keep adding water and see if we make any more progress towards our actual product. Alright, I've ditched out this horrible black liquid here. Even though I'm fairly sure it smells like our product, it's really not giving any of our products. So I put 20 mils of tertiary-butanol in here. We've got our sulfuric acid. I'm going to get this boiling first, and then we'll start dripping in concentrated sulfuric acid. Slightly different setup. Perhaps we'll actually be able to distill off some of our product this time. See, that looks good. Look! It's a drop. I mean, it could be water for all I know, but isn't it beautiful? Might actually finally be making some progress. Amazingly. The world's slowest distillation is actually being a success. Amazingly, we have some liquid in here. You know, a substantial amount of liquid. It's not tertiary-butanol, because tertiary-butanol's melting point is 25 degrees. It's also flammable, so it's not water. It also smells like, you know, natural gas. It's going, and it's going so slowly that I can just disconnect it and not fear about actually losing too much, because that's how slow it's going. All in all, it's been a very long day. Alright, it's about 11:30, which means I've been running this reaction for the last 5 hours, and this particular distillation for the last 3 or 4, I reckon about 3. We have some product, so now all we need to do is just get it out, weigh it, and then store it overnight, and we'll be done for this video. It's not a whole lot, but it doesn't come over very fast, and I don't think much is coming over at the moment. And I'm getting eaten by mosquitoes and insects. There's the biggest spider, non-huntsman spider I've ever seen that lives up there. It's nearly to the point I've got to give him a name. You can see he's feasting on a giant beetle there. Let's see if I can zoom in. He's huge. He comes out every night. I have that light on. He has a real good time. There's so many insects get stuck in that web. King of the jungle. Alright, back to the distillation. I have a flask cooling down in there that we're going to weigh into. Oh god, it's cold. Don't you dare evaporate. What are you doing? Oh, fuck me, it's cold. $102.9. Left over in the flask, there's actually a bit of stuff at the bottom and on the sides, but it's frozen, so it either has to be water, well, really tertiary-butanol is probably the tertiary-butanol azeotrope. It's good because the fact that it's frozen really separated it out from our product. Alright, and that's it. We have our final product sitting nestled in there in the dry ice. And hopefully it lasts until morning with some of the dry ice in there. And in the morning we can start the chlorination. Can't really do it now because it's midnight and I have to do it outside. As people have informed me, it's a lachrometer. Really makes you cry. Anyway, it'll be genuinely unpleasant. So it's not a kind of thing I can do inside, but lachrometer. Thanks for watching. I hope you enjoyed this video. It's difficult at points, but we got there. And I'm very happy. We actually got there. It's amazing. We did some theoretical chemistry and we actually managed to do it. Anyway, thanks for watching. I'll see you next time. Oh fuck, this Cody's out.